We are looking at a cost function, and in one of our handouts it was given as c of xy, and in Wolfram Alpha you have to enter that as f of xy. So I've entered the function. We are going to start by graphing this cost function, which is 3x squared plus xy plus 2y squared minus 15x minus 12y plus 75. The program will just plot this for you, and you can see here on the 3D plot that it looks like a kind of a bowl shape, and that means that the cost function has a minimum. So our cost is minimized for certain values of x and y. The contour plot confirms that for maxes and mins. This is what you would expect to see. Now, if we want to take this function and locate where the different derivatives are zero so that we can find the critical points, I would go ahead and copy that function, and I would say the dx of this function so this is computing the derivative with respect to x. So we find in certain problems or on a test, if you're doing this, you might want to record that the partial derivative with respect to x, so df dx, is 6x plus y minus 15. It is fairly easy to then modify this a little bit, change the x to a y, and also compute the derivative in the y direction. So take the partial with respect to y. It is going to be x plus 4 times the quantity y minus 3. In this case, we can kind of ignore the plots, but because we're really after those formulas. Now remember, the critical points really are those places where both of these partial derivatives are zero. And so one way to do that is to say solve, put that in parentheses, and so I'm changing the second one to a dy dx. So I am asking Wolfram to solve for the points where both the partial derivative with respect to y here and the partial derivative with respect to x are zero. I did find that putting parentheses around these equations actually helps. There are some cases where Wolfram Alpha might be not clear about what it is that you would otherwise be asking it to do. So put the parentheses in. Hit enter. And it is saying, well, what I'm solving for you is where x plus 4 times y minus 3 is 0, and at the same time 6x plus y minus 15 is 0. And it tells you that your critical point is located at the point x is equal to 48 over 23 and y is equal to 57 over 23. This is the critical point. We already knew from our first derivative, from our graph, that this is a minimum value. So it means that our cost is minimized when x is equal to 48 over 23 and y is equal to 57 over 23. You could then still continue and evaluate the function for these values, and you can do that by hand and figure out what the actual minimum cost is.